Stephen Seeley here with Ghost and the Windows 7 Allocator. Please welcome him.
Thanks, guys. Just before we begin, thank you for coming to the talk. I know it's the last one. Everyone wants to go home and drink and party, so it should be. And it's going to be a little bit mind-melting, so I'm sorry, maybe to some. But so just a quick show of hands of who's actually done any kind of memory manipulation or exploitation on any platform. Just a raise of hands. Okay, cool. That's good. Who's done it maybe on the heap? Any kind of heap exploit? Oh, okay, cool. There's actually a fair few. That's quite good. This is going to be interesting. So originally I had this talk as named Ghost in the Windows 7 Allocator, but because we're going to be covering a little bit of Windows 8 exploitation, or just the basics of understanding how it's actually working, and then we'll go into a possibility or a type of attack that could possibly work under the Windows 8. So I titled it just Ghost in the Allocator instead. So we'll start off with going, what we're going to be looking at. So why targeting the heap manager? We'll cover like some of the basic heap terms that I'll use throughout the presentation. Some Windows 7 heap theory, from the front end, and a little bit of the back end, but not too much. The LFH structures and the algorithms associated with that. Then we'll look at different exploitation techniques that have been done previously. I've only put a couple in there, two, because they were proven to be the most reliable when I was doing my testing and analysis and looking at how the heap manager was working. Then I'll continue on and I'll show you a new attack under the Windows 7 that I managed to get working that is more or less a basis of the free entry overwrite technique. So we'll look at more of that. And we'll do a bit of a demo, then we'll cover the changes in Windows 8, and then we'll look at a possible exploitation technique for that. So, who am I? Well, I'm a senior security consultant at StratSec. I do security research, and I also do pen testing. I'm a past member of a Corlan team, so these guys rock, so you should definitely talk to these guys for exploitation stuff. I'm not a software developer, and I don't actually have a C++ background or anything like that, so I'll just cover that quickly. So, why are we targeting the heap manager? Well, often during the process, a lifecycle, development, we see that a lot of early on memory corruptions are, wiped out. Stack-based buffer overflows, uninitialized variables, things like that. They're sort of wiped out early on in the development phases of an application, right? As versions increase, we lose those kind of memory corruption vulnerabilities. Heap overflows are a lot harder to find, and just memory corruption in the heap in general is a lot harder to find, just because of the dynamic way it's running, and because at the time of an overwrite or a time of triggering a corruption, you don't actually have the bug. The bug actually triggers there, is happening there, but the trigger is often not right there. It's often during using another chunk, later on in the application execution, or when a free occurs, or what have you, or collar size. So, I really do fear like a loss of heap knowledge in the industry. So I guess that's why I took this path in exploitation in the heap. And to help facilitate application data attacks, right? Because not always can you do an application data attack, or you might help leverage the heap manager to trigger overriding a specific object used by the application or that kind of thing. So, and of course, many other guys made it pretty cool. So I thought it was interesting from my point of view, anyway. So some examples of applications that have been done in the past with proper working remote exploits. You've got stuff that's done by HT Moore here, and Brett Moore did the Citrix presentation server exploit that abused the look-aside list and XP. And then you've got more recently, we've seen the FTP server from Chris Velicic using his free entry offset overwrite technique. And then there's a multimedia library exploit, which is an application-specific technique of incrementing or decrementing variable type and causing a callback on that variable. So I mean, I guess what do they all have in common, right? I mean, they're complex, right? So there's a lot against us in the heap manager, as you'll see. It's a real challenge, and there's safe unlinking now, obviously, since XP Service Pack 3, so much randomization in the heap. removal of pointers and, encoding, B-link validation when on the insert now from Brett Moore's free list zero attacks. Buckets are separated, no more pointers essentially in the heap so much. And now in Windows 8, there's now randomization on the chunk allocation pattern. So we'll just cover some heap terms just quickly. I'll just cover like a block is essentially going to be represented as 8 bytes. That's just how it's calculated in memory. A chunk is a continuous block of those bytes. So like when you talk about a chunk of, and then a size is represented by the number of blocks. So if you go a size of, 4, we're talking about 32 bytes here, things like that. So the determinism is the ability for an attacker to, influence the heaps process before or after a corruption. So to be able to lay out the heap state in a certain way to trigger the overflow and cause the right condition in the state of the heap. So, and a bin is just simply holding an area of memory that holds a number of chunks of the same size, essentially. So it's represented as called a bin. So we'll go on to a little bit of theory. We'll just look at like I said before, you utilize these bins of a specific size. The free chunks now have this thing in Windows 7, like the next offset, that allows it to work out where the next allocation is going to come from. So as that particular chunk's allocated, it updates another value called the free entry offset. And we'll look at this more a little bit later because it refers to the type of attacks we're going to be doing. Each heap subsegment has its own bin. So for example, a user blocks and a heap subsegment is a particular bin, and that might get filled up, and then a new one is created using the RTL low frag heap alloc from zone. Then there's this 8-byte structure for this heap chunk, and again I'll show you some diagrams in a bit, so it's not all confusing. You can activate the LFH very easily under the Windows 7 heap just by causing 18 consecutive allocations, and no more pointers like I said before. So this is the back end. The back end, I'm going to show you a bit of diagram here because it's just easier to explain. But basically the colors here represent the sizes. So you can have like multiple chunks of the same size, but the bin or the list hint here only points to the first chunk of that particular size. It has a B-link value, but the B-link is not a pointer like it used to be in the old heap, right? The B-link is actually a counter that counts and increments and decrements based on the number of allocations or frees, and as soon as that reaches 18 allocations or 17 allocations if there has been a prior allocation and free, then it will actually create a heap bucket and place that pointer in there. It'll actually be a heap bucket +1 for when it checks to see a heap bucket actually exists in that location there. So this structure, and then you've got the F-link, which obviously points to the chunk here. These chunks here, this is a single list. Note that. So on the old heaps we saw a free list like going across like this with different bin sizes, whereas now it's just a singly linked list like this with a B-link and F-link, and of course these are all validated now, these B-links and F-links. So exploitation of this is now dead, obviously. So what happens if there's a size greater than 1024 though, right? So like there used to be like free list 0 where you can insert the chunks. Nowadays it's in the list hint minus, it's actually the list hint bucket -1, I believe, and it's in the first blocks index, which there are 2 blocks indexes. If the second blocks index, let me rephrase. There's 1 blocks index by default, and if chunks are bigger than 1024, they'll be stored in here, and they'll be stored in order of size, and it will point to the first one. And if there's a second blocks index, then the chunks that are bigger than 1024 will be stored in the second blocks index in the list hints, as we saw before. Yeah, But the details of this is not too much important because we're going to be looking at more the front end side of it anyway. But I just thought I'd cover it for clarity. The actual front end, the low fragmentation heap, starts off by having a pointer to the low fragmentation heap from the actual heap base. And then it has another data structure here called local data. And then there's a local data segment info, which is actually an array of more management structures. So essentially it's like, it's just a heap within a heap, right? It's more management structures within and inside another management structure, which then is inside another management structure. But what we're going to be focusing on mainly is actually this data structure here. So, you know, that actually equates to this. And it has like a subsegment and it has a user blocks or user data header. And this is actually where the chunks are stored. There's a cached items in here, and there's a block zone as well, and that manages the subsegments for that particular bin. And there's also a free entry offset and depth to calculate how many allocations have happened in the low fragmentation heap here. So I'll just quickly show you. So these are the really important points to look out for. This heap entry here. And the free entry offset, this is actually used to exploit the heap manager from Chris Velicic. Yep, so this is what the actual chunk will look like. Essentially, it's got encoded bytes at the very start. The first 4 bytes are encoded, I believe. And upon an allocation, the next offset is overwritten because it's no longer needed. It's only needed when the chunk is actually free to point to where the next chunk is to be allocated from. This is like predictable for us from an exploitation point of view. This allows us some degree of control of where we know where the next allocation is going to come from. So that's an important point. As a bit of an example, we've got, we try to allocate a size of 232 bytes of a chunk, and it will look up the bin size of 1D, and then it'll look up the segment info for 1D, and we'll find its active subsegment, because a bin can have multiple subsegments from the LFH block zone, and we'll find that user blocks from that subsegment. And then once it finds that user blocks, it then can allocate the chunk from that particular user blocks. So I mean, if there's no more subsegments available, or if there's no more, if the active subsegment's not set, or it needs to create a new one, then it will call low frag heap alloc from zone, and we'll actually create a new subsegment and user blocks, and then force an allocation from that. Yeah. So it's pretty easy to trigger the LFH under the Windows 7. We pretty much know this. We can just cause 18 consecutive allocations. And that's some example code there, very simple, that will just do that. So this is essentially how it's working. You've got the chunks to be allocated. You've got a free entry offset down here that points to the first chunk. The free entry offset's calculated by using the next offset, or the offset to the chunk, and then times them by 8. And that will point to, and then if you do a user blocks plus this value, it will actually equal that chunk there. So and then there's a depth set in the aggravated exchange, as we saw before. So upon an allocation, the free entry offset's updated here, as we can see, and that next offset that was here is now written here times it by 8, gives you that, and that points to the next chunk. So essentially just works by updating it like that. Then if we have a free, it will work out what the next offset for that is, and write it into here, and reset the free entry offset. And that, in fact, that's actually one of the ways we're going to exploit it a bit later on. So we'll look at that exactly. So now we'll go on to the exploitation side of it. Ben Hawkes came up with a really good idea to trigger an arbitrary free, and that will allow you to free an object or a structure in memory that could have a function pointer and get called, right? And Chris Velisic also came up with the idea that you could cause an arbitrary allocation and allocate over the top of an object or a structure. So when I was playing around with this though, that I kind of worked out a way to work out that you can cause consecutive static allocations as well, using a variety of different ways to get into that particular heap state. So so determinism, I just cover a little bit about this because it's pretty important, but basically the idea is we want to have a predictable allocation pattern where we want that. We want to defrag the heap a bit. So upon we encounter an application that's running in the wild and it's got a heap overflow, but the problem is this heap, we don't know it's heap, right? We can allocate chunks to be able to just fill up the holes in the heap to make it to have deterministic chunk allocations afterwards, and we need a variety of primitives to help us in exploitation. That's just one, but we need a variety. We need possibly an info leak, a soft and hard leak of a controlled size. That's to defrag the heap, like I said just then. Arbitrary writes possibly, that could help us a lot. The ability to trigger a free when we need to be able to set a hole in the heap, maybe just before an object if we're using an application specific, if we're taking application data in the heap. The ability to trigger the heap cache might be really handy if we're exploiting the allocator via the heap cache. So, it really takes someone to work out what the application's doing. It takes you to work out, you got to reverse engineer the allocation process or the free process or that kind of thing, and work out, do you really control the size, or do you really, you might not control the size, or you might control just a range of sizes, from 0 to 20 bytes. There might be an integer overflow, but then it adds a header on, and then you control that just like a 20 byte range, so up to a 20 byte range. So you've really got to work out what it is you actually control to be able to get that. And we've got to be able to create arbitrary objects somehow, or nowadays anyway. It's very useful to be able to do that. And know that we're going to have function callbacks on those objects. This is really, really hard, and this is the hardest part of any kind of exploitation in the heap. So you can get the technique working perfectly against a particular application, but unless you set up the heap properly to begin with, then you are not going to get control of EIP, which is essentially what we want. So we'll cover Ben Hawke's technique first. This is a really, really interesting technique. Basically, the idea is that the chunk is marked as a segment offset chunk. When we trigger an overflow, we overwrite the header structures here, and we particularly target these two values here. We mark it as a segment offset, and then we set the offset to another chunk that we want to free, right? So essentially the overflow works like that. And we set the context value, which would be here, and this has to be below 3. Then this can be an arbitrary value here, this doesn't matter. And we set an arbitrary segment offset here. So I've actually, in this example, I've used bin size 5, which I wanted to go 2 chunks backwards, so I just times that by 2, and I set the segment offset there. So that's pretty much it. And then 0.5 will always be that value there to mark it as a segment offset chunk. So so this is really how it's working, right? So let's say the application, we want to go free chunk 3 from 0, 1, 2, 3, and then there is an overflow, and the heap and the headers are targeted, right? And we set it to this allocated object here, this segment offset here. So in this case, we're doing 3 chunks back. Then what happens is when that free happens on this chunk, it will actually realign the chunk header and free this one. And essentially we've got a situation where an arbitrary object or structure is freed, and we can possibly call a function pointer on that, or force the application to execute a function from that. So and then we allocate over the top of that, because the way the low fragmentation heap is working is it's first in, first out. I probably should mention that a little bit earlier on, but basically as the allocation pattern happens, an allocation and then a free happens like, in order, and then the last free is updated from the free entry offset. So the allocated, this will be the next allocation point. And once the chunk's allocated, we can obviously overwrite the V table and that kind of thing, and wait for a virtual function call or something like that. So, so this is basically the code the very simple code I came up with for Ben Hawk's technique. So, it creates a new badass Ben object. We allocate, and then we cause another allocation here. And this is the buffer we're going to overflow, and we're going to target this guy. So we overflow the buffer, and we hit our target, okay? And then it's very simple. We free the target, which is actually going to free badass Ben object. Then we overwrite badass Ben with this allocation here, okay? And then we fill that, overriding its V table, and then we call a function on it, right? So that sounds like a lot, right? But often, we'll be able to, we won't have to create the object, or if we do, then we can seed the objects in memory, or there's all sorts of, a lot of this is from the application's point of view. So we need to control maybe a little bit of this whole process, but not completely all of it. Now we'll move on to the free entry offset technique. The idea is that we overflow into an adjacent chunk, and we target the next offset, and that adjacent chunk will be free, right? The idea of that chunk is to be free. We target the next offset, and then upon an allocation, we overwrite the free entry offset, and then we know that the next allocation is going to come from the user blocks address plus the free entry offset, so we can set an arbitrary allocation. We can overwrite, an object and then call a virtual function on it. So it works like this. You do an overwrite and you set the next offset here, and then when you allocate this chunk, because there's no proper check on the headers, essentially you have the ability to set the free entry offset to this value here, which will calculate to that, and then we know that user blocks plus this value at user blocks plus that value will have an arbitrary allocation, so that will give us some leverage of control in the memory. So again, I'll go run through it a little bit of a diagram. So basically, you've got a situation where you've got a chunk where you're going to allocate from. That's the next pointer. And there's an overwrite on the next offset. The next offset's updated. When you allocate, it's updated to the free entry offset just here. And then that's going to point to an arbitrary chunk at a different location somewhere, right? The next allocation. And so when you allocate some other fake chunk or some other random piece of memory. So, the proof concept. So basically, it's very simple again. You seed some objects in memory. This will trigger the LFH and give us something to play with. We allocate a chunk. Then we fill that up. We target the next free chunk in the user blocks. Then essentially we allocate to set the free entry offset. And then once we set the free entry offset, we allocate again, and this will allocate over the top of an object, and then we just fill that, overriding the V table, and then force the virtual function call on that. So sorry if I'm going a little bit quick because I've only got an hour, so this is a lot to cover. So my attack came up with when I was looking at all this, and the idea that I came up with was, hang on a second. So if the free entry offset is updated from the next offset, then we might have the ability to set the next offset to match that free entry offset value. I actually was playing with the double free when this came about, so that's how I sort of came across the idea of this. So I'll just go through it. Basically, there's a couple of ways to obtain that state. You can obtain it from a double free, but the double free has to, during one of the second free, the chunk header is marked as a free chunk, and it needs to be remarked as either a busy chunk, or it needs to just be ANDed with 3F, so hex 3F. So, or you can trigger it via a free, and then use Ben Hawk's technique to free an arbitrary chunk. And you could probably try and free that same chunk again, or you could just very easily overwrite the next entry offset and do the same kind of thing as what Chris did. So essentially you know what the free entry offset is in the user blocks, right, at the time, or generally speaking you'd hope to know. And then you know, if upon that you pretty much set the calculated next offset here, and this, you know, pretty much you got the free entry offset divided by that value will give you the same value of what the next offset is, the same calculated value of the free entry offset. So those values will be matching, and then what happens is when you cause the next allocation, it will just update the free entry offset to the same value. But the thing is, the depth is still 29, right, in this case. So whenever you cause the allocation, it's going to keep returning the same address. It works pretty much like this. So you do the overwrite in this case, and you set it to be matching the free entry offset. And then whenever you do an allocation, you can force the allocator to keep returning the same address, because this free entry offset is updated to the same value over and over again. Yeah, boo-boo. But the thing is, when you're triggering it via the double free, you've got a situation where there's a test to see if the chunk is marked already as free. So you'd have to, if you need some sort of primitive where you can control that byte or a bit value from that byte, and to be able to make sure you can AND with 3F correctly when doing the double free. So my simple example, which is just using the double free, I could have done it via the overflow, but I just use this for the example. Just do 2 allocations, and then you free the second one, and then we do the not so likely overwrite, right? We modify that 1 byte in the header there, so it can be ANDed, and then we trigger the second free. Then that actually places that heap manager into that state now. So now every time we cause an allocation, it's going to return the same address. This allocation up here will return the same address as this allocation of the structure here. So these two will get allocated at the same address. The function pointer is going to be initialized. We overwrite that function pointer and trigger a call. So that's essentially how it works. Yeah, it works pretty well. So I'll just show you a little bit of a demo. It might be a bit easier to. So I don't know how well we're going to be able to see this. Okay, it's not too bad. So I just run in the debuggers just so I can set the breakpoints and show you how actually it's working, just to make sure everyone can see. So I just patched the PEB because I open up the process with the debugger, and I don't need the debugging heap on, so I just, fix up that. It's a little bit of a dodge. So 1 sec. Okay, so the first breakpoint set on the free, the second breakpoint set on the second free, and you can see here this is, I'm going to quickly modify something here, but up there, I don't know if you saw, there's a little bit of code to modify that header value, that offset +7, just here. So we'll see when we go cause the allocation, I don't know if you can see, but this is, the free, this is the actual chunk to be freed. This value should be modified, and from the free it's modified, and then it will get modified back to the same value or a similar value that can be ANDed with 3F. And then the second free occurs, which is passed on the check. Now every time we allocate, it's going to allocate the same address from this point forward, because the state's already been created. So we can see this is the allocated address here for this chunk. What is it? We'll set the other breakpoint on the other allocation so you can see the result. And you can see the second address there is allocated. The second allocation's occurred, and the address is the same. So I just put it as comments so you can kind of see it a bit better, but it might be a bit harder. And this is just the chunk here. So we're just watching this chunk very closely here. So now at this point, we're going to initialize the function pointer. Sorry, the function pointer is just there. And that'll point to .text code. And then if we let the application run, then it's gonna overwrite, you know, that function pointer there. And then if the function's called or a virtual function called, gain control of the execution process. So that's essentially how it works. So I guess one of the main advantages of this is the fact that you don't really need to set up a hole in the heap. If you want to target application data, you don't have to set up a hole in the heap before the object in memory to be able to then allocate that chunk and overwrite an object pushing forward. So generally speaking, if we're targeting an application using application data, it will be allocate to fill the heap and so we can get some sort of determinism, and then you will allocate an object afterwards, and then we free a chunk before the object, and then we allocate into that spot. We overwrite the object, but you don't have to set up the holes. But you still need to have the ability to allocate an arbitrary object, and you still need to know at runtime what the free entry offset is. So there is some limitations, and unless you cause an absolute large number of allocations, and so you can really work out what the free entry offset will be at runtime, then it's going to be a little bit difficult. But that's essentially some of the limitations of it. You have to know that the object you're going to force allocation on, you're going to force the override on has to have a virtual function call on it, or some sort of function call anyway. You're overriding a function pointer somewhere. You know, and then I got to Windows 8. Right, as I'm doing all this and I'm looking at this technique, and Windows 8 came along, and I was like, oh man, this is going to get hard. So, you know, and by the time I actually got to the Windows 8, you know, I could only really focus on the consumer preview version. I didn't get to the developer previews, but luckily for me, that was a good thing, because NTDLL changed a little bit. So I only looked at the LFH allocations and frees just briefly. So, but I noticed some changes. The first change that I noticed was the user blocks data structure here was changed quite significantly. A lot of members were added. Things like the first allocation offset, block strides, busy bitmap, and bitmap datas. This is quite new. And then there's this data structure here which has a pointer to this bitmap data here. And I was like, oh, that's kind of interesting. And then, you know, there's this guard page here that was added, and I guess this is to prevent any kind of modification of the user blocks. Yeah, so it's still triggered on 18 allocations or hex 12. You know, there's no more of this next offset or free entry offset, so the stuff you just saw before, it's now dead, like forget it, so don't worry. You know, it's now really randomized, right? There's a lot of anti-determinism in the heap. Chunks are allocated all over the place. We don't know what's going on. There's a guard page on the user blocks, and you know, there's this bitmap buffer which we have no idea how that's calculated or does or anything like that. So, but let's have a look at how the allocation's working, right? Let's go through this. So when we have a look, we can see that there is, first of all, it looks up a index value. And this index value is looked up from the heap data slot, and the index value is then used to look up random data or random byte from the heap random data array. Once that is obtained, then you know, the index is incremented and then written back into the heap data slot. We continue along, and what actually happens here is that there's comparison on the size of the bitmap to see if it's smaller than 32. So, you know, if we've got some chunks available that we can allocate from. at this point forward. Then what happens is that calculates this bitmap index, or that I called it, but basically uses the size of the bitmap times that random value that it retrieved out of the array, then divided that by 128, and gives you this bitmap index. And then once it's got that bitmap index, it actually updates this busy bitmap data, and then I kind of excluded that because it was quite a complex process and it's pretty randomized, and it's, we don't really need it. We need to know the actual mechanics of that just yet. So then once that's happened, the offset in depth is updated accordingly. So the depth is decremented if it's on an allocation, like it is, and rewritten into the data structure there. And then this is where it gets like a little bit more interesting, right? This is where we see like, this is going to be where the next chunk is going to be coming from. It sets like the block stride times, the bitmap data, which we saw get updated. And then it adds the first allocation offset. And then at that point, it adds the user block's address. All right, so that calculation again, it works like this, okay? So this is kind of important. This is how we can work out where, this is the point where you go, all right, what do I control? Where could I control data? Can I control any of this whatsoever? So I'll quickly cover the free because this is a little bit important too. So it still does this kind of thing. It validates the LFH block on the free. It works out, calculates the subsegment from a free, and if the subsegment couldn't be calculated, or if the calculated value mismatches the actual subsegment, then it will error out or it will cause memory corruption from that point forward. So that's pretty important. So if we're overriding, free chunks, allocated chunks, and there's a free occurs, then that's going to cause us a little bit of a problem. And another thing too, like the Ben Hawkes technique is now gone, right? So the fact that we can override an allocated chunk and try to free it to an arbitrary location, what's going to happen is that second chunk that it goes to free instead of the first one, that will actually be checked to see if that's also a segment offset chunk. And if it's not, then we've got, it's not going to free properly. But now we'll have a look at like possible exploitation under Windows 8. I say possible because it's not, it's still very hard to get 100% reliability, or at least some level of reliability that I would call fair, from our point of view. So originally when I was like playing around with this heap manager, I was having a look at like what members I can control, and as we saw, we controlled a couple of members out. We could possibly control a couple of members out of the user blocks, and I was like looking for like a D-word overwrite, because I knew I couldn't control where the overflow chunk would be. I knew that was broken, and I just thought, well, maybe we can just start targeting the heap manager for like certain D-word writes or a couple of byte writes that will just get us the right leverage we can use to get an arbitrary allocation or something. But then Chris presented at SciCan, and it was really good, and actually had an idea, it was really good, and to possibly overwrite the user blocks header. So let's have a little bit of explore of that. So the idea was that if you could overwrite the user blocks header, then you might be able to target some of those members and cause an arbitrary allocation. We don't determine where the chunks are in memory. It's completely randomized. And we generally, if we have the ability to mem leak in an application, to force allocations, that kind of thing, of a particular bin size, then we could essentially do more than just like 18 allocations or trigger LFH, right? We could probably do a fair number. So understanding that, we can have a look at the differences between the Windows 8 and Windows 7 on an allocation. We see that as we go through, an allocation is completely randomized in Windows 8, whereas it's pretty sequential in Windows 7. But note down here that the uninitialized user blocks, so this is not initialized at all until we reach this area. So as we go through, it we cause the allocations to occur. And then the user blocks is created. And then the chunk is taken from the user blocks. But what happens is if we could, what would happen if we could possibly target a user chunk to overflow a targeted user blocks? Yeah, we might have a little bit of an issue. But the fundamental problem with getting this technique reliable is we don't know the distance between the chunk that's going to overflow the user blocks because we don't know the order in which this allocation is going to happen. So this essentially we can't just overflow just enough to hit the user blocks. We have to overflow essentially the whole length of this data here, just in case the last chunk allocated out of this user blocks is from here. So that way we're guaranteed to hit the user blocks sequentially, all right? Pardon me. So this is the LFH block zone, and this is where the user blocks and things like that are stored. And as you can see, the subsegments are here. The very first user blocks is here, which is almost guaranteed to be filled up in an application. And you've got multiple user blocks after that. And the thing that we notice is that those are actually stored sequentially in order, and we can then possibly target those. So the idea is that we don't really want to damage this area here in memory. We actually want to target the user blocks directly. So we do it from user blocks 1 and target user blocks 2, right? Just like that. But note how there's no guard at this point here. So when I was doing the test cases, I was running against up to different user blocks, still no guard up to this point here. Possibly later on there will be a guard set and checked, but I don't think I worked out when the guard is actually triggered on. But in the test case I was doing, that there was no guard on these user blocks here. So this is how it actually looks like in memory. I know it's a little bit hard to see, but basically this here is the LFH block zone header. This is the user blocks pointer out of the subsegment. These are the 3 different subsegments. And this is the depth that we saw before. So once a chunk is allocated, this depth is decremented. Once a chunk is freed, it's incremented. So, yeah. So, we know that the chunks are not deterministic, but we now know that the subsegments or user blocks as well are actually deterministic. And that can provide us with a little bit of a leverage into exploitation side of it. So, as a little bit of example, it's a little bit, obviously it's unrealistic, but, we can trigger enough allocations to fill the first user blocks. We could cause more allocations to hit the user blocks 2 that we saw before. And then one of the chunks from the user blocks 1, we can use to target the user blocks 2, right? And then upon the allocation after that, we can trigger an arbitrary allocation. I'll show you how it works. This is essentially what we want to target. The first allocation offset, because we know that that's where the next chunk is going to be allocated from. These are going to be used to calculate where the next chunk is going to be allocated from. The block stride and bitmap, we need to set those to appropriate values, or at least control those values somehow, and set them to whatever to make sure that we get that arbitrary allocation. But the thing is that I noticed when I was doing the testing is that this busy bitmap pointer, the pointer for that, has to be writable, obviously, because it needs to be update the bitmap. And it also needs to, in my test case, null was proven to work really well, because when you times, obviously 0 with the block stride, it gives us nothing. So we can just control the arbitrary allocation based on the first allocation offset, which just makes it easier for when I was doing the testing. But essentially, you could set this to a pointer to a value that you can control. As long as it's static and is writable, it should be fine. So sequentially, the overflow works like this downwards. The user blocks header is here, and the most important members that we want to target are here in memory. So in fact, this one here is actually not important at all, really. This pointer is most important. So the thing is, the problem that we fundamentally have with this is that this here requires us a minimum of 12 bytes. Now, when we saw the overflow from the chunk that was overflown to the user blocks, from up here all the way down to hit the user blocks header, we don't know the distance, right? And so if we have an odd number of chunks in between that distance, then we might hit the members correctly from a sequential overflow, but if we have an even number of chunks, we might not. It all depends on the bin size that we're targeting. So we don't know at runtime where the chunk's going to be, the chunk's going to be allocated from. So we don't know the distance, right? So essentially, you could, like I said, you could set this to any value. You could set the pointer to null or any value as long as it's writable, and we should be on track. So that's essentially the members we control out of the calculation there. So yeah, we'll go through a little bit of a demo. Why not? This demo is a little bit. Oh no, that's okay. Cool. So yeah, so a similar kind of thing. We open up the application just in debugger so you can see the breakpoints being set and things like that. Patch the PEB. And the proof of concept code for everything in here will be released in the next week or so, just to let you know. So it makes it a bit easier for everyone. So when we run the application, we can see that we filled up the user blocks here, we filled up this one here, and we're using this chunk here to target the user blocks. And we're going to actually overwrite a number of chunks that have already been allocated. And that's what I was saying before, that if we can't control the free, if one of those chunks are freed, we're in some strife, right? We're in some problems. So here's the overflow that's occurred over the user blocks. And as you can see, there's sequentially overflow. We don't know the distance. We don't know how far it's going to overflow. And we have to make sure that these members are set at the offsets correctly. So we'll just have a look here. So this is the chunk that's an object, and this is the arbitrary allocation over the top. Note how. Yep, so it points to .text as we saw before, but note how it's not overwritten on the header, it's overwritten just beforehand. That's so it can be ANDed with 3F now, because the allocation routine now checks to see if it's a busy chunk already or not upon an allocation. So as we can see, the overwrite of the function pointer, perfectly, no problem, and then bang. You can still gain control of execution if that function pointer is called. So yeah, that's... Thank you. So like I said, the major drawbacks is we don't know that distance fundamentally. But having said that, there's a way to get around that possibly too. The major advantage of this technique, right, is the fact that we don't really need any info leaks or address leaks or anything like that. Still, all the randomization in the Windows 8 heap, we can still use a simple or straight sequential overflow and still gain somewhat reliable arbitrary allocation of an object and code execution. So it just goes to show that still, even though all the protection mechanisms exist, there are still possibilities for exploitation. You will most likely, like I said before, you will most likely overwrite allocated chunks, and in doing so, you make sure that those can't be freed. So yeah, like I said, the reliability is a major problem. So depending on the user block, the bin size will depend on whether we need an even number of chunks between the overflowing chunk and the user blocks, or whether we need an odd number or not. Because it has to be divisible by 16 eventually, right? It has to be divisible by 16 bytes, or 16 bytes, because the user blocks header, like I said, needs the 3 members, which is 12 bytes, but then you just add 4 to make it even between 8. So, I was thinking about this, like what the problem with has to be being divisible by 16. But looking at this really closely, you could actually possibly make it much more reliable by having the fact that you can overwrite with an 8-byte fake structure over the user blocks, and just sequentially overflowing just 8 bytes and not even using the 16 bytes. And you could possibly do that by having because the fact that the first allocation offset and the block stride is next to each other in memory, you could actually have those two values together that would hopefully also be a pointer to a static value that is writable. So if you could fill all those requirements of that, then you could make this a lot more reliable. So essentially that's, how it works. So I guess the conclusion of this is, like I said before, it's despite all the randomization and the protections in the Windows 8 heap or in the memory allocator itself, we still shouldn't fear possible exploitation of these evolving heap managers. There's still a long way to go. Applications that we want to target, or as people build heap exploits still today for under these sort of environments, we're going to hopefully see more metadata attacks or evolve application-specific metadata attacks like this evolve that can be used and leveraged a lot better against the Windows 8 heap manager. So pressing on, and even now, I'm having a look at a few other areas in the data structures a bit higher up that could possibly use to be leveraged for code execution. Around like the LFH block zone and things like that. So, I'd just like to say a thanks to a fair few friends and people, like especially the heap guys that have done a lot of work over the past on heap exploitation. It's helped me a long way in learning a lot of this stuff, and I hope that people continue it on and focus in on it. And some friends, some guys from Offensive Security and Corland Coder and Sinner and those guys, and my fiancée Vanessa, so thanks. Some references, and hopefully we have some time for questions. I'm sorry if it was a bit fast. So.
We've got 5 minutes for questions, if there are any questions.
If there are any questions, yeah.
Hi, Steve.
How you doing?
How realistic do you think it's going to be that Microsoft would implement cookies for heap chunks, basically? Or
sorry, say that again?
How realistic is it to think that Microsoft would implement heap chunk cookies, like placing cookies before heap chunks to avoid that if you start to override metadata, that it would check the cookie and see, okay, it's corrupted, I'm going to give up.
Okay.
It might, create overhead and make the entire application slower, but as computers become faster, then.
Yep. So a lot of the headers are already protected already. So that's, it gets encoded and decoded. As we saw, the first 4 bytes of the chunk header is already protected a lot, and those other values there are not used in a way that we can leverage as much as we used to anymore. As back in the old heap, we used to target things like the size, right? And that was easily leverageable because we could flip a bit, a bitmap or something like that. So, but now I think that a better thing would be maybe possibly either randomize the location of where the user blocks are, if that doesn't perform, implement too much performance or impacts, or possibly you could, come up with the fact that you could just set the guard page on the user blocks a lot earlier on in the stage, or through the whole thing. So I guess they don't set it on to a certain point because it might be some sort of overhead, and if it's a large application, it's causing a lot of allocations and things like that. It's going to fill up those user blocks already. So I guess that's why they did that. But I mean, if you could just do it for all the user blocks, then I guess it would really prevent the exploitation of this kind of thing. So I hope that answers your question.
Any more questions? No? Well, please thanks Stephen then.
Thanks guys. Cheers.